20, we ended up back at this concept of binary search. And I am going to move over to my handy dandy whiteboard. We'll see if I can get this working. You guys should all be familiar with binary search. If you played Guess the Number with your parents when you were young, or with your siblings now that you're older, the basic concept is pretty simple. And the reason we're going to talk about this is, well, there's two reasons. One, it's going to feed into sorting, and it also is the first something that isn't order of n or order of constant time. This is an order of log n algorithm. And I want to kind of give you an intuition for what that means, so that when we get onto the sorting algorithms, you'll have some feel for that. So the binary search, it starts off if you have a list of numbers or a list of anything that's in order from, you know, lowest to highest, for example. And the idea is, well, we want to eliminate the maximum number of things that can't be possibly correct with every guess we make. So we start off and we say, well, we'll set some variable low to point to here, right? So low is set to 0. And we'll set some variable high, right? 0, 1, 2, 3, 4, 5. So there are 6 elements in here. So we will set our variable high to be just off our list. So that'll point just to the end of the list. And we know, by the way this is constructed, that our answer has to be greater than or equal to, you know, if we're looking for the index of the answer, we know that it has to be greater than or equal to low and less than high, right? And that's kind of why we set it up the way we do. High's off the board, low is at the 0th element. So it has to be greater than or equal to low and less than high. Well, high is 6 and low is 0. If we want to get rid of the greatest number of guesses, right? There's 6 elements in our thing, 1, 2, 3, 4, 5, 6. If we want to get rid of the greatest number, we want to get rid of about 3. So we say, well, all right, so let's guess that, or let's check. We'll say 6 plus 0 divided by 2 is 3. So we'll look at element 0, 1, 2, 3, right? We'll look here, and we should probably pick a number. Somebody want to yell out a number? I can't see my thing, so I can't.
20.
7.
I heard 20 and I heard 7, so we will do 27. So the number we're looking for is 27.
Nice.
Okay?
Teamwork.
Exactly.
Heck yeah.
So we look at 27 and we say, is 27 less than or greater than or equal to or less than 21? Well, in this case, 27 is greater than 21, so we know it's greater than or equal to 21, right? So we know that we can't be in this part of the list. So we throw all that out and we move our low up to here. So low now equals 3. High we haven't moved because, well, we didn't need to. Right, and now we say, okay, there's 3 things left in the list. 6 plus 3 is 9. Integer divided by 2 gives us 4, right? 6 plus 3 / 2. Boy, you would think with all this whiteboard space I could have found a place to write this where it made sense. But we go 6 plus 3, integer divided by 2, right? That's 9, integer divided by 2, which is 4. So now we're going to look at, right, low is here, high is out here. We're going to look at space 4, which is right here. And we say, is 27 greater than or equal to 56? Well, the answer to that is no. It's not greater than or equal to 56. So that means that we can throw out this part of the list. Right? So we can get rid of those two. And now we know we'll move high to here, right? Because now we know that it has to be to this side of high, and it has to be to this side of low, including the value we're at. Right? So now we're down, we've thrown out these guys. First time through, we threw out 3. Second time through, we threw out 2. And now we have high is equal to 4. Low is equal to 3. 4 plus 3, integer divided by 2 is equal to 3. So we'll look at this value. I'm sorry. Yeah, we're done. We got it down to one. We got it down to one element. There's a stopping case in here that I kind of messed with. Let me just check out the stopping criteria on this one. Low equals mid plus 1. Sorry. So we actually should have moved this. Yeah, this test should have been greater, so we should have actually moved this out to 56. But I'm not going to go through that again, but that's kind of the concept of this, and you have to muck around with the indices, and what you'll see is that we've actually created an index that probably would never end because we would never get high and low being together. But the idea here is that we come through, and we always, well, you know what, I'm going to walk through this again. Sorry about that. We'll walk through this again with the right algorithm just to make sure that everybody gets it correct. And I'll pick new numbers. 0, 10, 15, 21, 30, 37. And we will again pick our target number of 27. We set low to be here at the 0th element, high to be off the edge. We pick the midpoint, 0, 1, 2, 3, 4, 5, high is 6. So the midpoint is 3, 0, 1, 2, 3. We look at 21. 21 is less than 27. So we know that since low is either going to point to the number or the number, if it exists, has to be to the right of low, we will set low to be here this time, which is what the algorithm is doing. So now low is equal to 0, 1, 2, 3, 4. It's set to be the midpoint plus 1. So low is equal to 4. We're still looking for 27. High is equal to 6. 4 plus 6 is 10. The high is 5. That's 0, 1, 2, 3, 4, 5. That's 37. Right, so we look at 37. 37 is greater than 27, so now we move high down to point there. High is now 5. Low is still 4. Before I go off the rails, just let me... Yeah, okay. High is now 5, low is now 4. We take the average, 5 plus 4 is 9. 5 plus 4, integer divided by 2 equals 4. So now we check 4 again. 4 is bigger than our number. So this time, instead of moving low, we move high again. High moves down to 4. High is equal to low. And we've got this down essentially to one place. And if we want to insert, if the number exists at all, it exists here. And if it doesn't exist at all, then this is where we want to insert it and move these guys down. All right, so that's what a binary search is. It allows us to find in a small number of moves where an object has to appear in a list. Okay, and if you walk through it, it's not all that hard to go through. We can instrument this a little bit, so you can. I think that's one of the practice exercises. But the key is this: the first time through the loop, we're able to make one comparison. In one iteration through the loop, we can get rid of all of these values, right? Depending on our test on 21. We would either get rid of all of these values or all of these values, right? So we're getting rid of about half the list. And every time we iterate, we get rid of about half the remaining values. So that means, right, if you're getting rid of half the elements every time, right? If there are 8 elements, the first time you get rid of 4, the second time you get rid of 2, next time you get rid of 1, right? So that's 3 steps to get rid of all of the non-answers. If you can get rid of half the wrong answers at every step, you're essentially, well, not essentially, you are exactly doing a log n algorithm, right? Because what you're doing is you're eliminating in one iteration half the values, right? So if you have 8, the first time there's 4 left, then there's 2 left, then you're done. 2 to the power of 3 is 8, right? So it's log base 2 gives you the number of iterations if you can get rid of half the iterations every time, half the wrong values every time, right? And that's kind of where this log value comes in. The number of steps you have to take if you can get rid of half the wrong answers every time is you have to take log n steps. And that's what this binary search algorithm does. I am you can see that I don't do this well going through these. I always get confused about whether low moves too far or high moves too far. But the concept is pretty good in there, and that second time through was actually correct. I would strongly recommend that you guys go through and do this practice, right? So if you go through here, right, the first time through the loop, this has 0, 1, 2, 3, 4, 5, 6. So this has 7 items in it, right? So the first time through the loop, we would be checking against 15.3. 15.3 is too much, right? It's bigger than 11.2. So we will bring high down to 0.2, 0, 1, 2, 3. Right? The next time, 3 plus 0, integer divided by 2 is 1. So we test on 7.9. 7.9 is lower than 11.2, right? So we move low up to 11.2. So now we have low pointing to 11.2, high pointing to 15.3. 0, 1, 2, 3 plus 2 is 5. Integer divided by 2 is 2. So 0, 1, 2, 11.2 is our test value. 11.2 is, in fact, not greater than the midpoint. So our test value is not greater than the midpoint. So that means we move high down, and at that point, high and low would both be equal to 2, and the loop would terminate. So walk through these, see if you can make sense of how they work. So anyway, that's, please, that's the kind of thing we need you, that's how you learn the binary search algorithm, is by walking through these. So I'm going to recommend highly that you walk through a couple of those on your own, and we'll certainly answer any questions if you have them. But that's just the way to do it, just what I was doing up there, only do it correctly like I did the second time, as opposed to incorrectly. You guys good with this, or do you want to do one more? Okay, I'm going to take that as a...
People are saying one more.
One more? Okay. My chat room was hidden. Okay, let me see if I can actually get this up on my board. We'll actually use exactly the one they want to do. Okay, so it's 19.1 is what we're looking for. Make a little note on a notepad for the values, and then we'll go over and do it. Had I been paying more attention instead of seeing this as just an exercise, I would have this up there. 1.3, 7.9, 11.2, 15.3, 18.5, 18.9, and 19.7. Actually, you know what? I have my printout of this lecture sitting right here. I don't know why I don't just use it. That would have made all of this a lot easier. And I better put down the Sharpie before I write on my whiteboard. All right, let's do one more of these. As a punishment to me for messing up that first time through. Okay, do I know which ones are particularly bad? Yeah, 19.1 looks good. Okay, so our L looks like 1.3, 7.9. Why I got rid of this was it was running out of ink. 7.9, 11.2, 15.3, 18.5, and 19.7.
Should you be on the whiteboard?
I should be on the whiteboard. I will navigate my way back and put you on the whiteboard in just a second. Our target value is 19.1. Okay. All right. So those are our values. Okay? And we're looking for 19.1. Hopefully you can see that up at the top there. Can we see that up at the top there? Yes, we can see that up at the top there. All right. So now let's take a look at walking through this. Right? So we set our low value to be 0. Right? So low points here. This is step 1. Let's be precise with our values. Low is there. High is 1 off the edge. So high is points to here. High is equal to 0, 1, 2, 3, 4, 5. Do I have all those? Do I have the right numbers? I missed 18.9. There's an 18.9 in there. 19.7. So high is 0, 1, 2, 3, 4, 5, 6, 7. Right? So high is equal to 7. Low is equal to 0. We calculate the midpoint equals high plus low. And this is an integer divided by 2, which is equal to 7 divided by 2, which is 3. Okay, so the midpoint points to 0, 1, 2, 3. The midpoint points to this value in the first step. Okay, so we take our 19.1 and we look. Is 19.1 greater than the midpoint or less? Is 19.1 greater than the midpoint? Well, 19.1 is greater than the midpoint, so that means that we can eliminate everything from here down. That just goes away. And to do that, what we do is we move low up to the midpoint plus 1. So our midpoint was 3, so low now equals 4. High still equals 7. We haven't moved it. We're on step 2. Okay, so now we calculate a new midpoint. The new midpoint is going to be 7 plus 4 is 11. Integer divided by 2 is 5. So 0, 1, 2, 3, 4, 5. So this is the new midpoint. Right, low is 4. High is actually still off our map. And now we look, is 19.1 greater than 18.9? The answer is yes, right? So now we take our low and we move it one past the midpoint and eliminate all of these people, all of these values. Okay, so now our low now equals 6, which, by the way, is the end of the list. And high still equals 7. We calculate the midpoint again. The midpoint this time is going to be 6. So we look at 19.7, and we ask, is 19.1 greater than 19.7? And the answer is no. So this time we move high down. High finally moves down, and now low equals 6, and high equals 6. And they both point to that value. And that value, if we want to insert 19.1, we would have to take 19.1 in and push it right there. Okay? And that would move 19.7 down 1, and 19.1 would go in slot 6 at the end of, near the end of our array. What happens if, instead of looking for 19.1 this last time, we were looking for 19.8? Right? Well, in that case, midpoint would have been 6, high is 7, the value 19.8 is greater than 19.7, and in that case, low would equal high would equal 7, and instead of moving high down to low, we would have moved low up to high, and the insertion point would have been at the end of the list, right? So it would have been an append operation instead of an insert operation. All right, and you can see that that was 3 steps, right? So 7, the next power of 2 is 8. 2 cubed is 8. So again, we are in a log n world. All right. Any more questions about that? Awesome. So let's go back to here, and let's go back to here. All right. So work through the last couple of those by yourself, or work through this one too without my hand wavy just explaining it. It's hard for me to. The whiteboard is not as convenient as it looks to get to. I've got a very, it's kind of like the genie, right? I've got a lot of cameras and things, but I have a very tiny space. Okay. This question, right? You don't have to come up with an exact number, but if we're dealing in a log regime, right, you would expect, 1,000. Well, next power of 2 is 1024, right? So you have 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So it would be about 2 to the power of 10. We'd expect no more than 10 steps. Now remember, we have 3 steps just for 7. When we get up to 1,000, now we're only talking about another 7 steps, right? So log n is a low number. It increases very slowly. 2048, 4096, 8192, 16K, 32K, 64K, 128K, right? So we're only adding another 7 to get up to essentially a million. So what is binary search used for? Well, binary search, right? We know that we can search. We know that sorting takes n log n time, and looking through a list once takes n time, right? So if you have a sorted list, you can use binary search to really reduce your search time. Instead of on average searching through n, or searching through an order of n locations, you can do it through an order of log n locations. So the two places where it's used is where you have to maintain a sorted list anyway, or where it's convenient to maintain a sorted list. For example, inserting a number into a sorted list is an order of n operation, so it only takes order of n time. It takes n log n to sort it from start, so if you have a big list sorting it, you have to make a lot of, okay. If you're making a lot of queries into a list to find out if people are there, binary search is much more efficient. So if you're making on the order of n queries, and a linear search takes order of n time per query, then n queries would take you order of n squared time. That's what you guys were running into when you were looking through the IMDb database. You were looking for stuff over, a lot of different stuff over and over again. So you were making, on average, an order of n queries into a list. Each query takes order of n time. So that's an order of n squared algorithm. If you have a sorted list, right, or if you have a list that's not sorted, it takes order of n log n time to sort, but then you can get by, you can find something in that sorted list in only order of log n time using a binary search. So if you're making a lot of queries, it's more efficient to sort your list first and then make the n queries at log n time than it is to make n queries at n time. Okay, so that reduces your algorithm from n squared to order of n log n. Okay, so does that kind of make sense? So that's what binary search is used for. Binary search is used to efficiently find things when, or find out that they're not there when you have when you have to make a lot of queries into, for example, a database. All right. Any other questions on that? Good, because now we're going to talk about it in kind of a little different kind of mode. So sorting is really powerful, and there's been a lot of, so searching was our first algorithm, right? And we talked about searching quite a bit.